Okay, let's see. So, I guess last time we ended talking about, where's that? I was connected, even though there's no one there. I guess it's fine. So let's just get started. So last time we just ended to talk about GANs. Just starting to talk about GANs, I should say. So, just a little bit review. Basically, just GANs is just a generative model that composed of two networks. One of them is the generator network. Maybe I pull up these slides there. One of them is the generative network that take some random input, then will output just some signal data images. And then we have another network is a discriminator trying to figure out whether the input is fake or genuine. And so, of course, this is a two-party game, a competitive game that will have a Nash equilibrium. And the Nash equilibrium that we are interested in is really when G generate data is indistinguishable from the training data, and the discriminator in that sense can only output true or false, whether it's genuine or fake, with 50%, half 0.5 probability. And last time we described the cost function for the discriminator and the generator. Discriminator we have cost function like that, and generator essentially just have it's just the negative of the cost of the discriminator. But because this part really the generator cannot control, we can ignore that. So therefore, the cost of the generator is just this guy here. I'm quite sure that should be a typo because it should be opposite side. Maybe this should be plus. Let's see. Need to check most likely. And then we also try to derive the optimum discriminator function, and that's basically ended there is simply like that. So if we know precisely the distribution of the data and the generator model, then actually the discriminator can have a optimum discriminator. Has a closed form expression for that one. So for the generator, actually the cost function is a little bit more flexible. As I mentioned, it can be either the negative of the discriminative cost. So then in that case, as I mentioned, if I ignore this one, then it will be just equal to this guy here. But a problem here is that note that at the beginning, assuming that the typical generator is much harder to implement compared to the discriminator. We all know how to create discriminator. We have previous half of the classes talk about how to create a good classifier. Right? Those are the essential discriminator. So most likely to start with, the generator will have hard time to fool the discriminator. So that means that DG set, DGZ here should be mostly 0, right? Because anything generated here should be identified as fake if the discriminator is doing a good job. If it's identified as fake, then D should output 0 here. So most of the time it should get 0. So that means this thing itself is most of the time will be just equal to 0 because you have log 1 minus 0 is just equal to 0, right? So then in that case, this cost function will be mostly 0. That means basically the gradient will be more or less flat. So you cannot train the generator efficiently in that region. So therefore, like an alternative, that's why we have this non-saturated cost. It is basically have a slightly different like cost function. We'll use this instead. So in this case, if for the samples that the generator is successfully through the discriminator, then like this guy will be more or less equal to 1, then like this will be more or less equal to 0, so we don't care about those costs there. On the other hand, if like for the places where like the generator has hard time fooling the discriminator, then unlike the earlier case here, like these guys will be pretty large. So minus log, this guy will be pretty large and have a pretty steep like gradient also. So you will have some information passing through back. So then of course, if your generator eventually become better and better, then if it's able to fool the discriminator most of the time, then you go back to the region where like it's here, right? Then would be the other way around. Then maybe you want to switch back to the original cost function. But on the other hand, like, maybe you can better yet ask like whether the discriminator is really doing a great job, because now the generator can fool the discriminator most of the time. So maybe you want to train the discriminator better to so that like the generator cannot fool it so easily. Anyway, this is just repeating what I was saying earlier, but mostly it's just like this figure, as you can see, like this. This is the original. Yeah, this is the original kind of cost function. Then like most of the time we will fall in this region, therefore it's not good to train at the beginning if the generator is not doing a good job like fooling the discriminator. So therefore like we can have a surrogate cost function like this non-saturating cost function here. So but if we move to this region now, then we should switch back to this cost function. So this is just some slight modification to begin with. And as I mentioned actually early today's class, the other class I also mentioned about GANs. And GANs is actually very hard to train, and it's notoriously hard to train. And there's lots of refinement trying to resolve those difficulties there. And I follow one paper like it's by Salimans in 16. Actually, the second author is Goodfellow himself. And he suggests several like good ideas. Actually, these several ideas, he suggests several of these ideas. And more GANs is actually in another paper by Google Brain. So let's look at some of these in the following. So the first one is this kind of one-sided labeling, smoothing idea. So okay, this is not a very kind of I should say straight notation here. It's a little bit sloppy notation just for clarity. So more or less our discriminator cost you can think of like that. Like you have for the true data, the discriminator should output 1, right? And we are essentially the expression we had earlier is computing the cost entropy of this guy with a delta function of 1 there. And if this discriminator actually output 1, then the cost entropy that will be equal to 0, then this will be equal to 0. And for the if the input is the fake data from the generator, then the discriminator should output 0. So anyway, this is basically just another form like to write our cost earlier for the discriminator. So one way to kind of I would say to improve the stability a little bit is like for the when the discriminator consider the training data, it just reduce the confidence a little bit. Instead of trying to say I should target everything I see for the discriminator, see the training data there, I'm 100% thinking those training data is true data or whatever, genuine data. we just lower the confidence to let's say 0.9. So this kind of makes sense. Just think of even though many times you see, even though you have this training data that you sample from real world, those training data can appear to be not completely genuine. My signature is a very good example. Every time it's like this, I just cannot make it consistent when I sign. So if you say okay, this is 100% is a signature from me, then it's very likely it's too confident. Even I cannot basically 100% sure this is my own signature. So therefore it's a good idea to just reduce the confidence a little bit. So of course you argue why we don't also reduce the confidence for the other side as well. So we saw the samples generated by the generator. Maybe we also want to say we are not 100% saying this generated data is fake. Maybe just give it 10% for that and so on. But turns out it's not a good idea that way. So you just want to do it a one-sided label smoothing. So if you try to smooth both sides, you eventually your discriminator, optimal discriminator will be like this. The problem is that for the region where that the x have a pretty small p data here, that is doesn't, at least at this moment, it doesn't look like it's a true data. Then the effect of this, because you have this p model here. Oh, okay. Originally we don't have this term, right? For the original one, when beta is equal to 0, we don't have this term here. But now if this is kind of small, we have kind of this fake stuff coming up that tends to have an undesirable bias. So anyway, I probably do not explain it pretty well, but this is the original statement from the paper. You can just read it. Yeah. Approximate G0 P model is large. Anonymous samples from P model will have no incentive to move near to the data. We demo for smooth. So in the sense you basically you won't have any weight to the. So basically when this is kind of small in the sense. So anyway, the lesson learned here is just don't do it. You may go back to that okay, yeah. So anyway, if you trust him, if you're interested, just read it more carefully, honestly. So and another issue is we always use batch normalization, right? It's good, but sometimes this is a kind of example. This is example generate some data. I don't know what kind of data. Maybe forest. I don't know what kind of training data is that. It's just it's I don't know. It looks like some pens or something. I'm not sure what is that. But as you can see, these have apparently this have you can see this is pretty different, right? It's from two different batch. Apparently, the batch information somehow sync into the GAN's kind of parameters and affect the data that you are generating. So so one approach you can do it to remove this kind of a little bit undesirable effect is we can either use a reference batch norm. In this sense, in this case, just meaning that you just use the same batch for normalization always. So you just fix one batch. I would say this is reference batch, and every time I'll just use that batch for normalization. We can also not go so extreme, and we can go for an intermediate approach. We have so-called virtual batch norm. That in the sense that you use the current batch and mix with the reference batch, and then do the normalization. Then also we kind of reduce these artifacts a little bit. And also one remark here is we need to be careful about balancing the G and D basically. you want to put more effort to train your D than your G. Basically, if your D is kind of stupid, then your G is rubbish. So you want to make sure that like you don't want to limit D to be being too smart. Trying to make some cases, like some simple approach would be like some researcher did is simply when you train the model, like just have more D steps than the G steps, and then it helps a little bit. And more precisely, like this is one effect that people kind of talk about quite a lot when they try to train GANs. Is like this mode collapsing artifacts. So for example, like I have a target, it's like this, but I may not actually generate data like this, but instead I just capture all the modes there. Like I generate data, just get into all these modes instead of getting this data instead. And this exactly, actually happen more often when you have a weak G comparing your D. So you want to have a much better D than G. And if you look at the the minimax game problem there, actually that is corresponds to like you have a strong discriminator. Okay, maybe I would just like not keep talking. I'll just let you guys think a little bit. So we have this minimax problem. You can either put the discriminator as the inner loop, or we can put the generator as the inner loop, right? So what do you think, like I should put the discriminator or like put the generator in the inner loop? If I want to make the discriminator to be smarter, should I have the discriminator in the inner loop or the generator into the inner loop? Do I make my question clear?
Discriminator should be outside. Generator should be inside.
You sure? So you mean like something like
B of G of C.
Kind of, let's say I don't know whether I should. Okay, it depends on. Okay, let us do both max. I just want to say both of them as score. So you mean like this?
Yeah.
Okay. Actually. Let's see. Why?
I think the output is dependent on the outside function, right? I think, I don't know. Because if the discriminator is the last function to execute, it can control the. I don't know, maybe.
Oh, wait a second. I better use the minimax here still because I cannot write max because they have the same score here. Let's say I have this. Okay. I cannot. Okay, I can write again. So I have JD is the discriminator score. Let's say I have D and G here. I want to. What I was asking is that like. This is the score for the discriminator, so we want to be maximize that. So I can have either do that by maximize D, and the G will try to minimize the score for the discriminator, so I will minimize G here. And alternative, I can also like do minimize G first, the same thing here, and then maximize D away. So go pivot for this one. So how about the others? Which one you think will be better? Like my hint is that like I would like to make the discriminator smarter.
I mean the second one. We have to maximize the D, right?
Yes. Oh, okay. So yes. You mean the second one? Yes. uh, actually, I'm thinking how to explain that. So you have the okay, because I have the slides. Maybe I have written something smart that I can. No, actually I didn't. So we actually should put a D in the inner loop, but that's how to see that. So think of like you are the G, right? So now you need to make the choice there. For all the I'm the generator. I need to pick my I pick my best generator or somehow I'm the one like going to pick the generator, and for whatever generator I pick, if this D is in the inner loop, it's going to maximize D will maximize the score for this target generator. Right? So therefore, in this case, actually, D is kind of like exhaustive. Like whatever like G, let's say me, whatever what I pick my G, D always have the best approach to kind of like target me, and this will be the other way around. And this one will be like benefit the G versus the D. So therefore, like if I want to make D to be smarter, like etc., should go for this way. So if you go for this way, what you're seeing, like if in terms of actual programming, D is supposed to be in the inner loop. So I should have like D in the inner loop and G is in the in the outer loop, and so forget about like whether inner loop and outer loop here yet first, but what we want to avoid is this kind of mode collapsing scenario, right? So one way we can do is like we can just have this so-called mini batch features. It's just trying to pick some of these features for each of the members that you have generated, and then like it's essentially just like see whether like based on these features like my new generated member is similar to the one that already generated. If it's too similar, then I will just discard that and generate a new one. So in the sense, will push myself as a generator to generate something new. So then it's very more likely not to collapse into a particular mode. Another approach is like based on this idea that kind of like doing inner loop for D is this kind of like by Google Brain is like this unrolled GANs. A high level will be like, so we trying to basically you think of like the what should I say? Here you have this D is in the inner loop, right? And inside here you're trying to maximize D, right? So you can, in reality, what you can, how you improve this D will be something like based on backpop and so on. You have gradient descent, right? So what you can do is simply you just do this like multiple times, or in this case like some kind of unrolling this like k times, and of course you can unroll it many times, like infinity number of times. Then in that case will be exactly equal to this guy. But if you unroll it k times, you will have like unroll k times GANs or something like that. And if you do it just one time, it will be the original GANs. So then like if you do this kind of unroll GANs, then you will get a better conversions. For example, if this toy example, then using the unroll GANs you will get into here, the correct target, but using the regular GANs you won't be able to get into here, get into the target. And so of course there are many works on GANs. Here I just sample some of those because it's from CS2 and I didn't prepare much. Um, and um, and that's another one that is mixing GANs with CNN will be like the DC GANs. So things is actually quite standard. If you look at that, this is like some highlight of the architecture there. Um, for example, they use batch lump. They didn't use the things I mentioned earlier, like just to avoid, for example, reference batch and so on. They use batch lump. This is earlier work. And they use valute and also like liquid valute. These are quite standard. They are also like stuffs that is common and popular as you see for like CNN, right? For example, like replacing polling layer with like fractional strike convolution. That's common in like besides in DC GANs and also like other convolution CNN works. And also like how removing fully connected layers and so on. And that's the generative network. So you start with some random vectors here. I'm trying to generate back an image, right? So first you go for a fully connected layer to get something like 4 by 4, 110, 20, and then you just expand that like with the convolution that we mentioned earlier, and then you expand that, like you eventually get an image here. And then this is training using a Elson dataset that is basically a bedroom dataset, and it's quite decent. Somehow like this one is really nice in terms of, I don't know, like in terms of generating bedroom, it's really very pretty. Actually, I just watched another presentation by Facebook Research like just last year, that they have another approach talking about like something generate. He doesn't. Here the Z is basically kind of arbitrary, right? He kind of like make some constraint on Z, and then trying to generate data. He have something like the result is pretty for the other data sets, for example, faces, but somehow he didn't do well for the bedroom data set. He didn't understand why also in the presentation. So this is, by the way, this latent variable, basically latent space, this is referring to the C vector there. Those C vectors can have like interesting meaning there. For example, if you pick two C vectors and you try to interpolate them, you can see like there's a change of kind of like continuous change of. I mean, it's pretty nice because you think of that like the image space is really high dimensional, right? If you have kind of like when you do dimension reduction from an image to a small vector, such as a PCA, and you have like continuous change of representation, or interpolation, I should say, continuous interpolation of this vector. It doesn't necessarily, when you map it back to the image space, it will give you a lateral image. PCA does it okay, not very well, but this one is actually doing pretty well. Like you do the interpolation, like everywhere it gives you a more or less a realistic image. And that's also like interesting arithmetics that in the sense like if you have, for example, like these images generated by different C vectors here, and this corresponding to smiling woman, then maybe I'll take an average of them and generate an average kind of image with like smiling woman. And then I have like another, I don't know, this generated pretty ugly. So anyway, it's a neutral woman. This looks like Michael Jackson. And then like this kind of average again have another like, image, right? And you can have like, for example, neutral man here. So you have a smiling woman minus a neutral woman plus a neutral man. What do you get? So logically, you get a smiling man, and that's more or less it. Actually, this appear like in natural language processing model also. This is like kind of like what's it called like word to vector, like that kind of word embeddings. Like you in that embedding space, you can also like play with that. For example, you have like queen minus woman plus man will get you king or something like that. Stuff like that. But this is kind of course, more interesting because the space appear to be much smaller, right? But the language space, you have only several characters there. But here you have an entire image, and you have more example here. Like you have like man with glasses, subtract man without glasses, plus woman without glasses. Then you get like women with glasses. Um, And so, but not everything is perfect. This is some failure case I borrowed from Goodfellow's presentation. One of his presentation is just like some GANs failure um, that it generated something, but all monsters here, like in this. This looks pretty like mother dog and kind of like puppy, but it's like more Picasso style. Uh, and all the rest also like it looks like have lots of eyes here, and I guess he also mentioned, I guess I agree with him, like since it looks like the neural network knows how to count but not count very precisely, it knows more or less to have a kind of a nose and maybe a mouth like eyes, but typically don't know how many eyes. I have more than like enough eyes here, and but the orientation is more or less correct. For example, you have nose here, the eyes here, they're more or less like, but then you have some more like, I don't know, yeah. And also, it's hard to have correct number of legs, yeah. And another interesting work is this stack Gant. It's not the first work trying to like, we have image captioning, right? This is just the inverse image captioning problem. So you give a task, a piece of text, just try to generate image, like based on that task. What he does is like he basically do this and also like have a hierarchical approach. Just start with like a smaller, generate smaller image, and then like try to kind of like from that smaller image and generate a larger image. And I won't go into detail of this, but I'll just show you the result is pretty nice. It's already 2 years old now. Apparently, that should be like follow-up work for this one. I remember the stack Gant Plus or Plus or something like that, but I didn't really check that. So, but if you look at that, like a small yellow bird with back crown and a short back pointed beak, and so it have like quite a lot of variation. But yeah, and you see this is the first stage and the second stage. The first stage, it looks like the first stage you have a draft, and then the second stage you put in more refinement there, more details, and that's also like another example. And let's see, flower, long, thin, yellow petals, and lot of flower. Is that typo? I don't know. Ender is what is that? Ender in the center. This flower is white, pink, and yellow in color and has petal that is multicolored. Yeah. Anyway, it's quite impressive. And another work is called iGAN. I'm sure like I'm not so sure. I think I'm not an artist that kind like graphic designer. I'm thinking that maybe some of this feature maybe even like appearing in latest version of like Photoshop or something. Like they basically like here you just like scratch a line and then it's trying to create a realistic image based on like your sketch or so on. And 2 years ago, I did play with the demos, but I don't bring my heavy computer, so I'm not going to. Uh, it's not fast, even with a GPU, it's quite slow. But again, like, because it's like more than 2 years old now, I guess that should be like update follow-up works for that. And so this is again old slides. I would say like this research on GANs is still continue. Like 2017, of course, lots of work in GANs. 2018 also, but basically, I guess despite all these very nice and impressive results, GANs is still like pretty difficult to train, and oftentimes like you have a new problem, you just have to run like 100 jobs there, maybe just pick the one that is actually running, and then just forget about the 99 of them. So yeah, yeah. So anyway, I guess that's what. Yeah, there's more links here like to for more work on GANs. So I guess I will just okay. That's one more slide for GANs, but I guess okay. There's some more pointers if you're interested, like for other works to stabilize GANs. There's some works like just to have like better loss function. And have this like conditional GANs. I on top of my head, I don't know what is that honestly. And of course, lots of applications. And okay, so I'm going to open a new topic yeah, again. So you guys have any questions, comments? So hearing none. So let's continue on something like it's still generative model, but it's not as new as GANs. Like we go back to history a little bit. So back to the 80s, we will look into Boltzmann machines. So Boltzmann machines were invented by Hinton, his co-author. And so actually it's like very much borrow like a physics model. You think of like just in statistical physics, like you can think of like you have molecule connecting to each other, like kind of like influence each other. And unlike all the models we talked about earlier, it's very much different, just different kind of beast. In the sense, it's not a feed-forward models. So basically, it's like a physics models you can imagine. Just think of like you have a physical model, you have molecules moving around. Right? The molecules will tend to fall into lowest energy states, and this is exactly trying to simulate that. So, and you basically, for simple case, let's consider a binary model here. So all nodes here have two states, just a binary states. And then the configuration, we have a number of configurations, right? So each of them can, for example, in this example here, each of them are binary. So we have 7 states here. So we have 2 to the 7, so many different configurations. So we have like 128 different configurations. And each of the configurations can have different energy based on their interactions. And then ultimately it should fall into the, not always, but have a high probability will fall into the lower energy state, right? And this will follow the Boltzmann distribution. That's why it's called a Boltzmann machine. And the energy function can be expressed pretty simply as this. So X will be the state for each of the node here, like as a vector. Like for example, like in this case, X will be 7 by 1 vectors. Right? We have 7 states here. Right? 7 by 1 binary vectors here. and MC will kind of control the energy for, you can think of like what should be the energy for wait a sec. I think probably makes more sense for x to take values -1 and 1, stuff like that. So and C will be just like to decide like whether it's more favorable for each of the state to be like positive or negative, so on. So you can think of this kind of like magnetic kind of like foreign force to force this. You can think of this as poles, like because of that, whether it's like more likely to have like a what's that, positive pole or negative pole? Do we call it positive pole or negative? I don't know. Anyway, so and then like across these states, they will kind of interact with each other, and this will be captured by this W here. So and overall, therefore we have this energy function, and as I said, like you want to prefer state that have lower energy, so therefore we follow this Boltzmann distribution here. So more or less, like the probability will be kind of proportional to this exponential minus EX here, your PX will be proportional to that. So because this probability, I just want to normalize that, therefore I put Z here. So I mean physics, they typically call this a partition function. And in this Boltzmann model, like Boltzmann machine model, typically you have some of these variables are hidden and some variables are observable. So some of them are visible, some are hidden variables. So how do you use that? Would be something like, for example, you can use it for prediction. You have like some of the variables are visible. Let's say this is your input, and then you want to know like what kind of output you will get. Then what you're going on is I will just impose this input to be, let's say this input should be 1 and 1 here. And then I just run this Boltzmann machine. It's just a simulation as a physical model. Right? As it runs, so then if slowly trying to converge, or like with higher probability converge to a lower probabilistic state, a lower energy state, high probability state, and then like and then this you can just like sample this guy as the output, right? And then you can, for example, you can use this, for example, for classification. You have a bunch of inputs here, and then you have some hidden variables here, and this can read out like the classification result, let's say. And this is a Boltzmann machine. The problem is like the Boltzmann machine here itself is actually a very powerful model, but it can capture lots of things, but when it's unconstrained, it's very difficult to train. So to train the model, basically we want to design this as WMC, right? But even to simulate the model itself, just imagine it's like very different from our previous models, right? Just to do a kind of prediction using the Boltzmann models is not instantaneous like a feed-forward models, because you need to wait to converge, right? You need to do sampling, so therefore like to train it is even worse. And consequently, I always mispronounce this word, or like I don't know what kind of accent I'm using. So consequently, then let's say 86, like Paul Smolensky like proposed this restricted Boltzmann machine, just a slight modification. And you probably heard of that. It's a very very famous model, restricted Boltzmann machine. And it's a very simple modification. Basically, it just disallow any connection, a self-connection within the hidden units and also the visible units. Basically, the hidden units cannot, like this units cannot connect to itself, and this cannot connect to itself. So all this connection, you just erase that, and also this condition just erase that basically. And this will be the restricted Boltzmann machine. And then I came up idea how to train the restricted Boltzmann machine, and then this model just become quite popular in mid 2000. And actually, this kind of directly lead to the renaissance of deep learning, actually, basically, because the first work that really attract attention is the Hinton's work. Have this like deep belief that used for. I will talk more afterward, like for like Amnesty detection that actually again is significantly better than the pi approaches. So the RBM is like this. So we have, as I mentioned, basically we have no self-connection in this hidden visible layer here, and then the energy function I can be write like this way. So I have only connection from the visible layer to the hidden layer, and this can be captured by this W here, and then the local energy for the hidden unit and the hidden unit and the visible unit can be captured by this CX and BH here. Then I can rewrite the probability, like again this is a Boltzmann distribution, exponential minus E over the normalization factors. So I plug in this, I have this here instead, right? So okay. I'll go slow because this getting more heavy on math like compared to the rest of the materials actually. So I'm interested to look into conditional probability. So why it's useful? Because what in practice, how do you train? I shouldn't say train even. How do you make a prediction? As I mentioned, is I need to do sampling, and the way to do sampling is using something called keep sampling. I'm not sure how many of you heard of that. So to do keep sampling, it's actually a simple conditional sampling method. Basically, you fix some of this random variable. Basically, fix all the random variables there, and then you will sample the rest, assuming you know the conditional probability, conditional distribution of these variables given all the rest of the variables, and then you just sequentially doing that. So then you have this as the new sample here. Then you assume this one is fixed as what you just sample, and then you have this as what you have earlier. Then try to sample this guy, and then you continue to sample this, and then you do it many, many times, and then you kind of converge to something, then that will be your output. Now to do this keep sampling, then I need to know the conditional probability, right? So I need to figure out these conditional probabilities here. I want to see what's pH given x here. And because there's no connection between this h here, these h are actually conditional independence given x. So now, I don't know how kind of you guys rusty in terms of this probability stuff. Like if you have any questions, just stop me anytime. So we here, this is when you here you basically have kind of probabilistic models. You can imagine something like you have two events here. This event is connecting to this guy. These is two different events. This event is connecting to a bunch of events here. And these two guys are not immediately connected. So therefore, given this thing here, these two will be conditional independence. And that meaning that you know independence, right? If you have something like x and y events are independent, then you have pxy, the joint probability is just px times py there. So now when we have conditional independence, let's say this is x, y, and z here, then I will have px y given z is equal to px given z. My handwriting is so bad. Times py given z here. So that's basically here. So because I have h here is among themselves, there are no connection. They are all conditional independence given x here. So this ph given x, I can write it as product of this one here. Now for each of these guy here, I'll show it in the next slide. Eventually can be written in the PT simple expression like this. And the other way one, I can also do that, like the conditional probability of x given h, because given h, x individual x will be conditional independence, so it can be written as a product of conditional probabilities. And again, I will show you guys that this can be eventually written out as this. So actually with this, then you can see that I can do Gibbs sampling rather easily. So I will fix all of this x here. Let's say I start with some x here. Let's say this will be my input samples. Let's say maybe I have the sum of the sample, like some x here, and for the other x I don't know, I just put in some random values here. Then I will just go for each of these h, right? Start from here. So I will just sample according to this distribution, this probability. Then I sample one at a time, sample all of them. Then after I sample all the h here, then I will flip to the other side. Then I will try to sample. Okay, this guy I fixed x. I'm not going to touch this. This is my input. But then I will try to sample these two guys here, right? Then I will have new sample for these two guys. Then I will go back to this step and try to sample h again, and then just go back and forth. Then I will have the sample of x. So now we need to figure out this, why this is equal to this and that. So then basically, so let's start with the conditional probability ph given x. So I didn't bold it, but this is like the vector h and the vector x here. The conditional probability, of course, is just the joint probability over ph, right? pH can be written as this guy here. Basically, just marginalize the joint probability. So I'm summing over all the h here. So therefore, sorry, I have this is not pH but px, right? px can be written as this here. So and phx, the joint probability, as we know earlier on, is just this by Boltzmann distribution. And then, so the term below the denominator is, I can also write like this. Then the normalization factor just get cancelled. And also, like, if you look at that, this is sum over h, right? And this is also like above and below is the same, also got cancelled. I can erase that. So I only have these terms here. And also like for, okay, I can write the sum here. If I look at this W here, it's basically a matrix, right? But let me just write W as a stack of like row vectors, like Wi here. And then this product here, then I can rewrite as H, basically H transpose is equal to H1, H2, and so on, right? Up to H something, right? Hn, let's say. Hm, actually, it should be Hm. And then, like, this multiplied by Wx. Of course, like Wx here, like, I will just get Wx is actually W1x, W2x, and Wmx, right? As a row vector here. So therefore, like, if the product here will be just become the sum like this, right? So because then if I do the product, this is H transpose this is Wx, then is when I do this product, it's just H1 W1x plus H2 W2x and so on and so forth, right? So therefore get this one. And it's very similarly, I have like B transpose HI can also write as a BHI. So I just basically expand everything. I do the same thing for the denominator as well. And also for the summation here, I just expand that. Like I sum over a combination of vectors of like 0, 1 vectors. I have length m, but I can consider it as a product of sum, right? So I just sum over each of the individual digits there. So, and then, okay, I just copy that. Let's see, what's the difference of this and this? Oh, okay. Yeah, sorry. When you're getting old, it's so weird. Like you look at something and you don't. Actually, it's like my cat. I guess I'm not sure. I'm thinking like I'm just getting senile, like because of my age, or like just because I have my cat. I got that. What's that called? That parasite, like toxo. I forgot. Yeah, I'm thinking about that because I heard news also saying that will affect your brain somehow. I'm sometimes I think my cats are pretty okay. They are both pretty smart and sometimes pretty stupid. Of course, they shouldn't be really smart, but sometimes, for example, my cat is he loves cat grass a lot. But whatever I'm holding this kind of like circular plane, apparently it's not a pot, right? It's actually a bowl. I mean, thought that is a pot or something. Then it will just like keep begging, like I want to eat something, like eat the cat grass, but it's not cat grass. I might put it down and look at that. So it's not like that, but I hold it up again, but he's yelling again. I'm not sure what he's thinking, but anyway. So, but I feel like sometimes I'm like that. So anyway, so it's okay, but yeah, this is nothing, right? This is okay. This is nothing. So then I just continue. This is just algebra. Right? I split that. This is product of sum. Oh, sorry. This is sum over this product, but I can just expand as a product of sum, right? So it's like from sum of product to product of sum, basically. So then finally I can regroup the terms. Regroup the terms is like that. Then I can put back this like C transpose X and Z back. Then if you look at this guy, each of these only depends on like HI. And this is actually very nice. And you look at that, this is exactly actually is the conditional probability of HI given X. And that's therefore you know that okay, this actually the probability the conditional probability HI given X is supposed to be like just like that. Right. Yeah. Right. Sorry, it should be like that. What I mean is like, so and then I have this here. I just copy the terms from previously. Then now I remove this CX again. Like I get this here. And then this is sum over H is like 0 and 1. Actually, I use H is 0 and 1 instead of 1 or minus 1. Then I have this guy here, and then this, as you can see, is just basically a similar function. Similar bi plus wix. Therefore, like what we got what we have claimed earlier. So of course, like for the other side, also it's the same way. If I have pxi equal to 1 given h, it's just equal to sigma ci like plus like I forgot like maybe wi transpose x, something like yeah something like that, yeah, so w transpose k, something like that. So but the other proof is more or less the same. So then, as I mentioned, like data generation is like give sampling, right? I already mentioned that you can just sample like H, and then sample X, and then sample H, and sample X, and so on. Here is you can compute the marginal probability again, but I guess I won't go into detail again. More or less the same step. So you can compute the marginal probability with, you know that this is like the probability of like pxh here. Then I get the px itself. I should marginalize, so I sum over like all the possible h there. So as I do that, eventually, if you go through the algebra, I should have an expression like this. And this, I just copied it from the previous slide here. By the way, this function have a name for that, like this log 1 plus exponential something. It's also called the softmax function. It has a kind of a form like this. It's actually basically the integral of the sigmoid function. And this whole thing here, like in terms of x, you can also, like in physics, they have a name for that, called energy function, like free energy function. But yeah, once we have the px, then we can do the actual training, right? Because for the training, you actually, I'm not sure. Okay, maybe I'll continue this slide and then I will stop here. So, we'll use the, okay, assume that you have some training data here. So this is the training data set here, T. So, and we know that, like, given a model, W, C, and B, we want to fit this model such that this training data will have higher probability, right? And we do that like using the cost of entropy loss. So in the sense, we hope that okay, let me just repeat, like I'm probably not very clear here. So let's say T is the training data here, right? T is the training data here. So in the sense, the training data set, you have T that contain, let's say, like T1, T2, and like T is not the training data. T is the index set of the training data, I should say. So therefore, like I have basically, I have the training data is like x1, let's say x2, and x, basically T here. And then all of this training data will kind of like, you observe this as your data, right? So if you think of like you have the probability kind of like should similar to what you are looking at for your training data, the distribution of this training data basically will be like each of these have a probability 1 over T, right? So, and for the rest, we'll have no observation there. So, or something, if you, let's say if I have just T is equal to 2, I have like two data points there. So I will have like, let's say this is like one of my training data is x1, I have another training data is x2 here, and both of them like have probability 1/2 here. So I want to have a distribution kind of match with this guy, right? And my target distribution is like this P here, right? So then the cost entropy between this guy and this guy will be the, if you remember, will be equivalent to kind of the Carroll divergence between the probability of the P of that one there with okay, I feel like more I saying I'm making it more confusing, is that So let's see. Yeah, okay. Maybe you just accept that like this is the cost entropy. I guess then you're happy. But why this 1 of t is like from here? You're fine with that? If you don't remember, you probably need to go back to the first lecture slides that we actually, I remember that we did derive the cost entropy loss there. That is based on Carroll divergence. And if you assume one of the distribution, the other distribution, just uniform distribution, then actually I should say like the cost entropy is like that, right? Q log P. Okay, actually I can just say like that, right? Q log something like that, right? If I remember correctly. I mean, in this case, the Q is just equal to 1 over T. Therefore, we have expression like this. And then and then we can substitute that what we derived earlier. We have this, the marginal power distribution that we derived earlier, right? Is equal to f, and with this, let me go back. We have is equal to this expression here. So therefore, we substitute into that. We have this here. Now then, we supposed to kind of like minimize the cost entropy loss. So therefore, we take the derivative with respect to those parameters there. And then we basically will get something like this as we take the derivative with respect to this guy here, right? We have this log theta here, and for this guy, when I take derivative of this log c here, I will get something like this. You can go through the algebra. Actually, it's pretty simple. You have this. But if you look at this, this is kind of interesting though, because this term here is actually just equal to px, right? So therefore, like this is actually is the expectation of this guy here. So therefore, like I can also rewrite this as this minus this guy here. And so in terms of training, you actually, the gradient itself is the difference of two terms. People sometimes call this is a positive phase and negative phase. So the positive phase there, okay, is not with respect to the sign, but it's like, if you look at this here, this is like related to your training data. You're trying to have your basically your distribution to get close to the training data, and for the negative phase, it's trying to get the distribution to just for the rest of the samples, just to not actually the rest, but for everyone, including itself, just to minimize to kind of like the distribution to, or like I guess a pictorial way will be like this. If I have distribution like that, maybe if I have training data like that, I'll push up here, right? That would be the positive phase here. But for everyone else, I would just push it down, right? Including itself. Then will be like have the negative phase there. Yeah. So okay, we will just continue next time. So and probably repeat this here a little bit next time.